Hello, everyone. My name's Chris. I'm one of the room hosts here. I just have a couple of housekeeping items before we get started. Just so you're aware, the emergency exits for this room are out the back door and to the right. If you need to use the restroom, again, it's out the back door, and it's a couple doors down to the left. Just one reminder to make sure to please silence your cell phones. And at the end of the session, please be sure to rate it using the mobile app. This session is speeding up scientific computation with Astrophysics. And so I'd like to hand it over to Antonio and Marco.
Good evening, everyone. My name is Antonio Corina, and I am the Amazon Web Service Account Manager looking after universities and public research institutes in Italy. And I'm very excited today to be here and to introduce the case of the Italian National Institute of Astrophysics, which is a public research institute that conducts research in astrophysics, ranging from exoplanet, gamma ray astrophysics, and radio astronomy. My first interaction with the institute took place a couple of years ago, and they told me that their biggest problem in order to conduct their research was to have servers, so compute powers, to be ready in minutes, to be ready to scale up and down quickly, that they didn't want to invest in hardware, and that they had a small budget available. After that, we start proof of concept in order to test those requirements. And I still remember how surprised and happy they were with the result we obtained. In fact, after that, we start our collaboration for two projects. The first one is related to design instrumentation for searching for other planets outside the solar system, while the second involved simulations aiming to study the violent universe by detecting gamma rays. Those projects both required high computational power and storage with high throughput in on-demand mode. And overall, the benefit that INAF received by using our services were first to have a cost-effective solution. In fact, they paid only for the resource they used. They had small budget, and they spend a couple of €1,000 to run important projects like this one. Then they had the possibilities to develop an infrastructure that was easy to use by its researcher, even those without high-level skills in IT. And then they had the availability to have the right resource when it needed in on-demand mode. So I'm really, really proud about this story. And I'm really proud that we were able to help them and other institutes like them that with their projects can impact the world. Today, by using our services, scientists and researchers can analyze, store, and share large amount of data, focusing only in science, without focusing in server, and with a small budget. So I'm very, again, happy to present Marco Landoni, PhD researcher at INAF, which in person tried our services and led those projects. Thank you so much. Hope you enjoyed this story.
Thank you, Antonio. Can you hear me? Okay. So, just to set the agenda for all of you, today I will tell you two stories about the couple of projects that involved us in our journey toward the cloud, and in particular to the AWS platform. And I will introduce you ourselves, so who we are, first of all, and then we'll tell you two stories. The first one is related to the design of really complex instruments for searching extrasolar planets and possibly detecting biosignatures in their atmospheres using EC2 and CUDA really parallel code. And the second one will dive you into the world of gamma-ray astrophysics with Amazon EC2, SQS, and Amazon Lambda. So we will join together all these services to solve our problem. So who we are, first of all, INAF is the National Institute of Astrophysics in Italy. It's a national public research aimed to carry out, promote, and exploit the scientific and technological research in the field of astronomy and in astrophysics, and to promote and favor also internally and develop a technology toward and inside the industry. Like in this case, we had a very tight collaboration with AWS, and to pursue excellence at international level. And when we talk about INAF, especially in Italy, we're talking about astrophysics. Our institute is headquartered in Rome with 17 structures all around the country, and we have a very strong connection with university, both local and international university like the Harvard, the CFA, Columbia University, and so on. And we have a lot of professors and university personnel associated to INAF itself. Just a couple of words about our roots. So where we are from, let's say our first observatory is the one in Brera, founded in 1764, while our roots in science are coming back from Galileo Galilei and Giandomenico Cassini, Schiaparelli, and other people that greatly increased our knowledge in astrophysics. Couple of words to me. I'm from the Observatory of Brera, which is an observatory related to INAF, our national institute, that it is based in Milan with two different, let's say, agencies, two different observatory. One, it is in the heart of the city in Brera, while the second one, it is in Merate, near Lecco. Our infrastructure today, we are involved both in ground and spaceborne missions. And from the ground, we are involved in the optical wavelength range with the ESO VLT and LBT, and our national telescope, which is the Telescopio Nazionale Galileo, which is based in Canary Island. From the ground, again, with the radio band, with SRT, which is a radio telescope based in Sardinia, and with ALMA, and in in the band of gamma rays astrophysics with MAGIC, which is an experiment in La Palma, and so on. But we're just looking at the tomorrow future with the ELT, that will be the very extremely large telescope from ESO for the European Southern Observatory, 40-meter large telescope with the radio, with a square kilometer array. And CTA for the gamma ray astrophysics and gamma ray observation of astrophysical sources. So let's start with the first story today. This is our background. This is where we are coming, and the first story is related to the hunting of habitable exoplanet with the extremely large European telescope with HIRES. HIRES is a spectrograph. I will introduce you what is a spectrograph, so what is our business in some sense, and how we solve the problem to have a simulation really, really fast to assess the performance of the instrument. And I'm proud to say that HIRES is a project, is a very large international project led by Alessandro Marconi, a full professor at University of Florence. the idea of the existence of exoplanets started from maybe Giordano Bruno in the 7th century, and saying that probably stars harbor extrasolar planet. An extrasolar planet is a body that is not able to sustain nuclear reaction that orbits an host star. And Earth, for example, it's a planet, or Jupiter or Saturn, and we are looking for these kind of bodies outside the solar system, aiming to detect probably the biosignature from complex life. So this is what we thought it was a rule. So our, let's say, backyard, our solar system with our planets that we know pretty well, but we come to the great diversity of various exoplanetary systems coming from different missions, from Kepler, which is a NASA mission that discovered a lot of different exoplanets with different physical characteristics, and from the ground using spectroscopy or imaging. And this is a sort of routine. I just like to give you an idea that also some artists started to produce posters. I have one of these in my house, so it's quite common today. And we know that one star over 3, more or less, or harbor an exoplanet. So this is quite impressive. But how do we hunt them? There are different techniques using both imaging, so looking at the light of the star, and using spectroscopy. So we are used to say and to think that when a planet orbits a star, the star is not moving while the planet orbits the star itself. This is not actually true. In fact, both the star and planet orbit together around a point that we call center of mass. And in the case of a solar system, or mainly for many different extrasolar system, 99% of the mass is concentrated in the star itself, of course. So the body center of the system, it is in the star. However, if you are a distant observer, you will see both the exoplanet and the star orbiting as in this figure. And if you look at the light emitted from the star, you will see a very peculiar feature that we call Doppler effect. It's something that we are familiar with. That it's like an ambulance. The frequency of the sound is different if the ambulance is going toward you or it is going far away. And the problem, or I mean what we exploit in this case, is that we decompose the light in the various different frequencies, the various different colors. And the light emitted from stars is not continuous, has a lot of absorption lines. There's black lines that you can see here due to the cold gas that surrounds each star. This is also for our sun. It's quite common. And looking at the movement of these black lines in an image, we could recover the speed of the star along our line of sight, and with Kepler law, recover the mass of the planet. So we're looking at images that are decomposed in various frequency. It is a thing that astronomers call spectrum in this sense. And using this movement, which is a very, very, very tiny signal in the detector, we could recover the mass and the presence of the planet itself. Just to have a rule of thumb about this, our Jupiter induced about 12 meters per second to our sun during its orbit, while in the case of Earth, we have 9 centimeters per second. So let's think about a fly of a mosquito of a body that has a mass of 10 to the 30 kilograms, which is really impressive. And we can do that. And we would to push further this. We would also try to characterize the exoplanets. And we need very, very complex instrumentation. But before building instrumentation, we have to do simulation to be sure that we're able to do that. And I will introduce you how our journey to cloud helped a lot in this sense. Our IO data stream, since we are more or less computer scientists or very interested in computer science, cloud computing, and so on, our IO data stream is basically a telescope coupled with a spectrograph. These are actual images. This is the very large telescope from ESO in Chile, and this is a spectrograph Espresso that it is installed at the moment at the Observatory of Paranal in Chile, which is the European one. So how does it work, a spectrograph? As you remember, we have to decompose the light. You have a star with a distant exoworld. Stars emit ray of light straight. If we consider that star is at infinity, so distant, we collect it through a telescope in this case, and using a system which is a bit complex, I would not to spend too much time on this, we put the light in an optical fiber. And if we look at the end of the optical fiber, we will see a white image, because it is the sum of each color of each frequency emitted by the light of the star itself. But if you have a spectrograph like a prism of a rainbow after a thunderstorm, you can decompose the light in each different component. And what you will have at the end, you will have a different image for each color of the same fiber. And in the end, you record this on a detector. So just to let you know that the various images of the fibers, in this case, are overlapped together. So it's a continuous signal that it is recorded on the detector itself. This is an actual image from HARPS, which is a spectrograph that is running right now again in Chile, but with the smaller telescope, 4-meter telescope from Switzerland. And if you see this image, you will see this line. And this line is the decomposition of the light of the star itself in each elementary components with the image of each fiber. And if you look carefully, you will see the famous black lines, the absorption lines that we use to detect the presence of the planet. This line with the spots are used for calibration. I do not want to bother you much on this. But it is used to calibrate your image in the wavelength. You have to know which wavelength, which color is in the CCD, because CCDs, the detectors, are black and white. And using proper data reduction, we recover this band that we discussed before, and we recover the presence of the planet. So we just measure the movement of the black lines along the detector. This is not very simple, because if you would like to detect an Earth on a star which is similar to the Sun, you have to detect a variation of 1/10,000 variation of pixel on the image. So it's a very, very difficult task. This is already a day-by-day reality, because we're doing this with Espresso, which is the new generation spectrograph that will be able to detect Earth-like planet. But the problem is that we would do much more, as I said before, because we are looking for planets in the habitable zone. And we will be able to detect that with Espresso, but our final goal, as I said before, is to study their atmosphere, because we would like to understand their chemical composition, to better know how is their formation history, and to maybe better understand the formation history of our solar system, and to detect signatures that could reveal complex life. We will not see the green man on that exoworld, but we will see the probable signature in the atmosphere coming from organic molecules, for example. And to do that, we will need the extremely large telescope, which is a telescope that it is going to be built again in Chile. I'm sorry, it's the best observatory that we have at the moment for the sky condition. And the extremely large telescope will be a 40-meter telescope. And just to let you know how big it is, just to compare the Big Bang with the ELT itself. So to do that, we will use HIRES. That will be a very, very complex spectrograph composed by various detectors, 72 fibers, different modes of observation, a lot of interfaces between the telescope itself and the instrument. So how we could be sure that we will be able to reach our goal, we have to do simulations. And this is the fact that triggered us to the adoption of the AWS cloud. So the problem is that simulations are required to check hardware design with respect to the scientific return, as I said. And the hardware design changes very quickly. It's quite common that some optical engineers say, okay, I changed this lens in this optical path. Please, could you check that we could detect the biosignature in the spectrum at the end? You need a very accurate system and fast system to answer this question. And the phase A, which is the first stage in the design of the instrument, lasted for about 1.5 years. Our journey to cloud, so we developed a simulator that we call end-to-end simulator, which is composed by different modules that simulate both the telescope interface and the behavior of the atmosphere, the behavior of the exo world, and the optical fiber link properties and so on. But at the end, we have to simulate image. And this is our bottleneck. Why? Because to simulate a full high-res detector frame, we need to simulate it, as I said before, the image of each fiber for each wavelength with an accuracy that we discussed before, better than 100 parts per million pixels. And this is just a simple image. It seems to be simple, but the problem is that to render this, you need a lot of computational time just for one. I will explain you in few moments. You have to think about this. You would like to study and understand how the light falls in each pixel for each fiber, for each wavelength. That's the goal of the simulation at the end. Oops, sorry. So we reached our goal by dividing this image that we call illumination profile by 10 pixels per 10 pixels. And if you have to do this, you have to calculate a very, very nasty integral. I do not want to show you, it's pretty scary, but you need a lot of 4 cycles and so on. So it could be really, really computational heavy to compute. And to reach our goal for the accuracy required, we have to divide again by 10 some pixel per 10 some pixels. And if you do this with the single thread, with using a single CPU, you end up with 60 seconds for just one image of the fiber, for just one illumination profile. So the problem is computationally heavy because the detector frames need the accuracy that we discussed before for each image, and it is composed by there more than 1 billion of each image fiber. So this is a very complicated task. But the good news is that each fiber image is independent from each other. As I showed you before, the images are overlapped in some pixels, but you can store the image of each single fiber and add it up at the end of the computation. So this is the good news. So first of all, we would like to parallelize the computation of each single image, and then we will distribute using the cloud. So we use, in this case, the CUDA using Amazon EC2. We use the G3 instance with Amazon EC2, and in this case, we use Spot instance also for the first test. And we used the paradigm of block and threads to perform our simulation. In particular, we assigned to each block 100 threads needed to compute the surface integral. It's an integral at the end. It's a double for loop in this case for each pixel, and each subpixel is computed by a single thread. The good news is that since this image is independent from each pixel to the other, you could do this, you could do this in parallel. So we ended up with a couple of, let's say a factor of 100 or more adopting the NVIDIA CUDA for rendering our illumination profile. This was really, really, really useful, and we spent a lot of time to develop the kernel, which is the function that it is spread over the CUDA cores to speed up the computation. And then, since we used AWS for our job, we used this instance for our test. It was pretty simple to scale it up in this way. In particular, we start from a list of a single fiber image. So you have to consider this input as a list of 1 billion, for example, half a billion, depends on the mode that you would like to simulate, of different image illumination profile that you would like to simulate. So the optical engineer starts by uploading this to S3, and as soon as the upload is started, we have an AWS Lambda function that it is triggered after the upload that could prioritize the computation. So it could be quite smart to see, okay, has been done in another simulation, or we need this before another simulation that we're going to perform, because we would like to check every configuration of the hardware, maybe because we would like to measure a very, very tiny signal, as I said before. And so in this case, this function is also in charge to use and to instantiate a spot fleet with a pre-configured AMI image, which is a very simple Amazon Linux deep learning image that worked pretty well also for the development at the beginning, because we had all the proper library and the CUDA libraries set it up properly to focus just on the development. And in the end, each illumination profile is sent back to S3, and then it could be summed up on premises. Oh, okay. We also move the all data on Glacier just to reduce the amount of the cost, of the overall cost. This is a sample result. It's pretty similar, and in fact, we reached the accuracy needed in this case for high-res, and we published this paper. I will come back at the end of the talk about our link with papers and AWS itself, and we were able to simulate this in a few hours. So it was quite impressive to combine the computation with CUDA and the scale up accordingly to the size of the project itself. So in this case, you can see the object itself, the famous vertical absorption lines that are used to detect the planet, and the calibration light. As you remember in the image of HARPS or Espresso is the spectrum of a particular calibration lamp that we have to calibrate the image itself. So how did the AWS Cloud help the HARPS team? First of all, during the development phase, it was crucial to have a machine completely ready without buying the hardware, and we could also we had also the possibility to test different GPUs against our code with all the libraries pre-configured on the proper AMI. And the scalable architecture allowed us to explore the full simulation of the system, fulfilling the requirement for the phase A, from weeks per simulation to hours per simulation. That was really important, especially for a phase A instrument that could change pretty quickly, and you have to answer pretty quickly if you are in the scientific requirement of not against a certain setup. And we greatly, of course, optimized the cost, and we consumed about 5 million CUDA core hours in this case without using a local cluster. And the phase A is now closed, so we didn't buy the hardware, so we are happy at the moment because we just paid for what we needed at this stage of the project. And phase A has been closed successfully just last year. This is the first story, and we hope that our project will continue in this sense. We will have a phase B, I don't know, maybe in the next years, but we plan to give to the community the instrument as soon as possible and follow up the Earth-like planets detected by Espresso to see if biosignature could be revealed by ARES itself. The second story is completely different. As Antonio said, our institute ranges from radio astronomy to exoplanet to gamma ray. And in the second story of our journey to cloud is related to gamma ray astrophysics in the cloud with the Cherenkov telescope array. So why gamma ray astronomy is important in this case? We talk about extrasolar planet and maybe extrasolar life. Gamma ray astronomy is important to study the violent universe. In our backyard, for example, with galactic supernovae, or in other galaxies by studying growing black holes. And how we detect the high energy gamma rays from the ground? We use a physical phenomena that it is called Cherenkov light. Basically, when a gamma ray comes from an astrophysical source to the atmosphere of our Earth, it starts an electromagnetic cascade that produces charged particles. These charged particles that travels at a speed faster than the light in the same medium emits blue photons, so very, very bright, or very, I mean, not bright, but very, very short blue flashes on the atmospheres. And using these blue flashes that are called Cherenkov lights, we could recover the energy of the incoming photons from the astrophysical source, recover the position, and study the source itself. This is a tricky approach. We use optical telescope, particular optical telescopes that must be very, very fast to see the sky and to detect this kind of events that last for nanoseconds, more or less. So we use silicon PM camera to do that. And we will use in the future the Cherenkov telescope array that will be an array of telescopes with different size, ranging from 24 meter for very faint events to telescope of 6 meter for very high energy events. And INAF is particularly involved in the last in the construction of the prototype of the last of this last kind of telescopes. And using this observatory, will be able to study the universe also for the faintest sources and for the most energetic sources. So we could also test some fundamental physics in some sense. Just to give you an idea of the problem, this observatory is expected to generate approximately 100 petabytes of data for the first 5 years of operation. Why? Because if the astronomical source emits, let's say, one event, you will have a background from cosmic rays, from other charged particles or background coming to the Earth, that it is really huge. And you have to disentangle between the signal and the background itself. But when you observe, you cannot do it on the fly, mainly. So from the level 0, we call, so from the raw data, in some sense, we will have some algorithm, intelligent algorithm in this case, to disentangle between actual events from the astrophysical source and the background one. This is already done with current Cherenkov telescope facility like MAGIC or HESS or Veritas, and we will do this also for CTA. As in the case of IRES, simulation of astrophysical sources must be done in order to access the performance of these facilities. So we would like to ask ourselves, we are able to see this galaxy with this particular spectrum. Can we do that with these kind of telescopes, with this background and so on? And as in this case, we would like to do it quickly. We used for our simulation the official software in the context of extragalactic astrophysics. So we concentrated mainly on the growing black hole in this case. And we did it for many sources with great results, and thanks to the architecture that I will show you in a moment. So what is a simulation in this case? You start from the model of your source, which is an XML file, really, really simple, that contains all the parameters of the spectrum of the source. Then you generate a list of raw data events that contains both the events from the source and the events from the background coming from the sky. You analyze the simulated data, you reconstruct the model, and then you compare. This seems quite simple, but if you do this with a very crowded background, with a very faint source, with an observation time of 50 hours, you could end up with 40 minutes for each simulation. And you cannot do just one simulation in this case. Why? Because when I say that you compare the model, usually you compare, for example, basic properties of the source that we call flux, for example, which is how many energy is emitted by the source itself. And this histogram, I will tell you what is saying in this slide, say that you need a lot of simulation to properly assess the parameter that you would like to recover from your instrument when you will observe your source. In particular, if you observe a source that is really bright, we call it Crab. Crab is the Crab Nebula, it's a supernovae in our backyard. It's a standard candle that it is used for assess the performance of this instrument. Maybe you can do it with just one simulation. You can see this black histogram is very tight, so you do not have a very large spread in the fluxes that are reconstructed. But when you go to, for example, to millicrab or 0.1 crab in flux, you have to think about luminosity. You have to do your simulation many times because the background starts to dominate. You have very few events, and you don't know which is the actual flux that you reconstruct. So you have to do this, for example, 1,000, 2,000, or 10,000 times. And just one simulation needs 40 minutes. You could have many sources to test again. Maybe you would like to test and publish a paper to say, okay, we could see these kind of galaxies. You could have many different spectral types, different sources and physical properties of the source itself, different background, instrument setup, etc. So you end up with thousands and thousands of simulations in this case. And the good news is that also in this case, we have an embarrassingly parallelism paradigm because each simulation is independent from each other. So this is the proposed architecture on AWS that we use to perform our simulation. You have to think about that the simulation is more or less a list of commands to be performed. In fact, we have just one command because we used proper software to combine the pipeline in this case. The pipeline from generating event and reconstruct the model. But everything, again, starts with S3. So scientists upload their XML files that describe the source and the list of simulations that they need to run and to test. And as soon as the file is uploaded to S3, an AWS Lambda is triggered, and all the commands, in this case, are pushed in SQS queue, and this is AWS Lambda is quite smart to, again, to assess what kind of simulation to test, if there is some possibility to optimize in some way. And at the same time, it starts to instantiate a spot fleet with a pre-configured AMI, and in this AMI, we have all the software needed to run the Cherenkov telescope array simulations and all the files that describe the response of the instrument against, for example, spectral sources. So we have everything in our AMI. And this is scalable because this AWS Lambda is quite smart to assess how many instances of virtual CPU we need to perform our HTC computation. In this case, it's HTC. There is no message passing between instances because each process is independent from each other. And at the end, the output is sent back to S3. In this version, we collected all the events that we simulated. So we had, at the end, various terabytes of data to save the generated events, to test again, to see if we could improve the reconstruction of the model and so on. And as in the case of HiRes, we have a life cycle on S3 to move the data to Glacier, in this case, to reduce the bill at the end of the month. We have also a second queue that we use for that we call failed queue in some way, that it is used to push back simulations in charge of an instance that has been marked to be terminated. We never ended in this situation, actually, but we have also this possibility. And at the moment, it is done by hand, but it never happened. We have a reloaded version of this using also AWS Batch because we containerize the software using Docker. So we containerize all this suite from CTA that is the software able to produce the events, analyze the data, and reconstruct the model. And we containerize it with the response function of the instrument, that the calibrations and all the response from the instrument itself. And we use, in this case, AWS Batch with the Amazon Container Registry to continuously improve our architecture. And in particular, in this case, this is a beta version. We are testing right now. So we are doing for a particular bunch of simulations. But in this case, the computation starts by uploading the same XML, only the XML file on S3, while the job definition is defined in AWS Batch, which is pretty simple. And then AWS Batch is pretty smart enough to create an auto-scaling group with EC2 instances properly optimized to reduce the cost in this case and increase the overall throughput. What it is important to say is that at this time we do not store all the events, but we use DynamoDB to save the parameters, for example, the flux or the spectral properties of the source at the end, and we reduce also the amount of data that it is stored. It is important to say that this is for a particular approach, because I will give you in the take-home message for me, each problem, especially in astrophysics, has its own computational model. So this works pretty well in this situation. So the benefits, we were able to run thousands and thousands of simulations by deploying this architecture in minutes, accordingly to the needs from the scientists involved in this project. And we optimized the overall performance by a factor of 100, and we consumed about 500,000 CPU hours simulating terabyte of data events, and we use, as I said before, smartly the resource. ENAF has its very large on-premise facilities for the HPC and heavily parallelism simulations with message passing. And since each computational model and problem has its particular architecture to be solved, we were able to smartly use these resources. For example, in the case of cosmology, we use our on-premises facilities because they need a lot of message passing in this case with a lot of CPU cores, while for HTC or burst use, we found that in this case the AWS platform was performing pretty well. And remarkably, we published 4 papers, and varied proceeding is just 1 year by speeding up this computation and smartly using our resources, both in cloud and both in premise, of course. And AWS has been also part of our research with our teams. We published a couple of papers. The first one, it's published on Astrophysical Journal. We're proud on this. And you can find all the details on the implementation of the architecture that we mentioned before. And the second one, it's a small review in some sense of application of cloud computing in astrophysics with AWS in this case. So our conclusion and take-home messages. So it's just the beginning. And as I said, each computational problem, especially in astrophysics, has its own optimized model to be solved. We saw a lot of different architecture during this meeting, really interesting. And it's important before solving a problem to say what we really need to do that. And in this case, we found that AWS platform, especially for the HTC workload, performed to be and demonstrated to be a powerful solution for a number of computational astrophysics tasks. And this is a growing situation. So there are a lot of colleagues in ENAF and in other institutions that maybe could need burst simulations, so on-demand computational power for HTC workloads. So it's quite important to start to use this kind of technology that, in our case, performed pretty well. And as I said, our situation is really increasing in this sector. That's all for me. Thank you, and I hope to have give you an overview of our two projects that involve the AWS and for two mainstream projects of our institute. Thank you for your patience and to come here. Please.
Thank you, Marco. Thank you for your presentation. I hope you enjoyed this case study, and I would like to ask you if you have any question. Marco, we are happy to answer to your question. Thank you so much, and enjoy the rest of your day.